So, good day. Next portion is effect of impact loading on ductile material and its application in forging. Okay, so a body or a structure member may subject different types of loading. The loading may be a static type, or the load may be a dynamic load, or it's a, for example, in case of a tension test, a body subjected to tension test in a UTM machine. So in that case, actually we apply a static load. Okay, the load is just gradually increasing from minimum to maximum. Okay, so that is a static load. But the dynamic load, this continuously varying. Okay, so impact load, the impact load is a nothing but it is a dynamic load. Impact load. That is a type of dynamic load. Okay, so an impact load is a dynamic load where load is actually applied very suddenly. Suddenly it is applied. For example, can you give an example for an impact load? Anyone? The load which is acting suddenly on a member or any structures.
Forging.
The?
Forging.
Yeah, during forging, during the hammering chamber, then actually hammering, this is my workpiece and I am applying a hammer load. That is an impact load. Okay, suddenly we are applying a load. Any environmental natural loads, any type of natural load acting on a structure?
Lightning strike.
In the?
Lightning strike.
Lightning the time with it. Okay. Then what about the earthquake? It's an impact load, right? So suddenly it is applied, okay, and it's a very huge amount of load. So this type of suddenly applied load, what is the nature of the material when this type of impact load acting on a material? Okay, that we are studying in this area. So when a material is subjected to this type of impact load by an intense blow, for example, in this type of hammering, we are applying intense blow on the material. Okay, in which strain rate is extremely rapid. Okay, that means the deformation with respect to time is very high. In a very small amount of time, we are applying huge amount of load and thereby huge amount of deformation. So the strain rate will be very extremely rapid. And during that time, it may behave in much more brittle manner than observed in the tensile test. That is very important. Even a ductile material behave like a brittle material during the time of impact load. Okay, but if you take a ductile material for a tension test, UTM machine, okay, that is a gradually applied load, that is a static load. So we got a result which is almost similar to a ductile material. But when we apply in this UTM machine, when we apply or in any other case, if we apply an impact load, this ductile material behave like a brittle material. The fracture will be like a brittle fracture. Okay, so that is the important criteria. So its effect is much greater than that of steady load of same magnitude. Okay, maybe this ductile material, for example, in case of 100 Pascal, we applied a 100 Pascal stress. So there is no huge deformation or there is no fracture for this ductile material when we apply 100 Pascal as a static load. But when we apply the same 100 Pascal on the same material as an impact load, there may be some fracture. So the behavior of the material will be different based on this type of load. So impact test is used to measure the toughness of the material. We already discussed what is toughness. What is toughness?
Energy absorbing capacity of the
energy absorbing capacity of a material before fracture. Okay, how much amount of energy is absorbed by a material before fracture, that is toughness. Okay, so the impact test can be used to measure the toughness of the material. Okay, how much amount of energy can be absorbed before fracture by a material can be measured using an impact test. So, for example, I take two specimen, specimen of material 1 and specimen of material 2. Okay, and here in both cases I am applying a impact load, and I'm applying an impact load on these two material. Okay, and in this material I am applying a particular amount of X amount of energy. Okay, for the so when I apply X amount of energy, it's fractured, or X amount of impact load, it's fractured. And here in this I am applying Y amount of impact load or Y amount of energy. At that time it is fractured. So based on the amount of energy or amount of impact load applied, we can measure the toughness. Okay, so we can use the impact test to measure the toughness of the material. For in these two material, if this one has more energy absorbing capacity, then we can say it has more toughness. Okay, it will only fracture at a very higher amount of impact load. Okay, so that is the measure of the energy absorbing characteristics of a material. That is the toughness. Okay, that is the area under stress strain diagram up to fracture. Area under stress strain diagram up to fracture. Okay, so high toughness is exhibited by the material with a high strength and a ductility. Okay, so it should have high strength as well as it should have high ductility. If the material is brittle, then this will be the graph. The area under this graph is only this much. The toughness will be low. So for a ductile material, this is the graph. It has more amount of area or more toughness. It will be more tougher material. So ductile materials are more tougher than that of brittle material. Okay, so we have to use a ductile material when it is used for a impact loading condition. Okay, for example, നിങ്ങൾ ഒരു ക്രോക്കറി പ്ലേറ്റ് എടുത്തു. ഒരു ക്രോക്കറി പ്ലേറ്റ് നിങ്ങൾ ഒന്ന് ഡ്രോപ്പ് ചെയ്ത് എന്നാ സംഭവിക്കുക? അത് പെട്ടെന്ന് സഡൻലി ഫ്രാക്ചർ ആവും. Because that is a brittle material. It's a ceramic material. It's a brittle material. So there is no impact loading capacity for a crockery material. Okay, നമ്മൾ suddenly drop ചെയ്യുമ്പോൾ actually what type of load is acting on that material? ഒരു impact load ആണ് അതിൽ ആക്ട് ചെയ്യുന്നത്, അല്ലേ? So when we apply an impact load, suddenly fractured. Okay, so brittle material has less toughness than that of ductile material. So for example, നിങ്ങൾ ഒരു ductile material ഇട്ടു. ഇപ്പോൾ for example ഒരു steel member ഇട്ടു. It will not fracture because it has a capacity to absorb energy, or it is a more tougher material. Okay, so during the impact load, the ductile material with the warts and cracks will behave like a brittle material, and it is not indicated in the tensile test. So even a ductile material during the impact loading conditions, some of the material may behave like a brittle material. Okay, so we have to do impact test instead of this tensile test. In the UTM machine, actually we are doing tensile test, right, where we are actually applying load in a static manner. But we have to do impact test to determine the behavior of the material, whether it is a ductile, whether it is showing a higher toughness or not. Okay, so that is the importance of impact test. Can you give an example for any type of impact test?
ISOD and Charpit.
Yeah, ISOD and Charpit test are the two types of impact test. Actually, നിങ്ങൾ അത് ചെയ്തായിരുന്നോ ലാബില്?
Sir.
Okay, so there are two types of tests, the ISOD test and the impact test. Okay, we will discuss about that. So a brittle material requires less energy to break and hence lack toughness than pure ductile material. Already discussed, brittle material has less tougher than that of ductile material. Impact tests are particularly useful for finding the ductile to brittle transition characteristics of the material. I will explain what is the ductile to brittle transition in the next heading. So the main objective of the impact test is to select the material with a high fracture toughness. So by conducting the impact test, we can identify a material which has higher toughness, so that we can use that material for a impact loading condition. Okay, so that is the importance of impact test. By impact test only we can identify which material has higher toughness or which one has lower toughness. By means of the static UTM machine test, we cannot identify which one has higher or lower toughness. Okay, we have to do this type of impact test to identify the toughness of the material. So you may know what is forging process. This is called forging process, and forging process can be do by two methods, either by applying impact load like blows. Okay, by hammering this workpiece. We can see this is my workpiece. By hammering on this workpiece, I can change the shape and size of the material. Okay, and this is a one type of forging process. Another type of forging process is this one like a pressing. Okay, here we are applying actually a static load. Okay, gradually we are applying a pressing load on the material, but here we are applying impact load during the hammering process. Okay, these are the two type of forging process. By forging process, we can create any shape of the, we can change the shape of the raw material. Okay, so that is the forging process. In the forging process, actually we are doing, so which one is has more efficiency, more effective? Is it impact loading or pressing load?
Pressing load.
Gradually apply ചെയ്യുന്നതാണ് impact load act ചെയ്യുന്നതാണോ better? ഏതിലായിരിക്കും കൂടുതൽ ഡിഫോർമേഷൻ ഉണ്ടാവാൻ ചാൻസ്?
Impact load.
Yeah, impact load ലായിരിക്കും. So impact loadന് higher effectiveness ഉണ്ടാവും during the forging process. Okay, കാരണം press ചെയ്യുമ്പോൾ that is like gradually increasing load ആണ്. But in case of impact load, we are suddenly applying the load. Okay, what is the timing? ഒരു നിങ്ങൾ ക്രിക്കറ്റിൽ കേട്ടല്ലേ what a timing എന്നൊക്കെ. What is timing of a ബാറ്റിംഗിന്റെ ടൈമിൽ ടൈമിംഗ് എന്ന് പറയുന്നത് എന്തുകൊണ്ടാ? ടൈമിംഗ് ഷോട്ട് ആണെന്നൊക്കെ കേട്ടിട്ടുള്ളത്. എന്താ ടൈമിംഗ് ഷോട്ട്?
പെർഫെക്റ്റ് ആയിട്ട് അടിക്കുന്നു കറക്റ്റ് ടൈമിൽ.
അല്ല, ടൈമിംഗ് എന്ന് പറഞ്ഞു കഴിഞ്ഞാൽ എത്ര ടൈമിൽ അത് ആ ബാറ്റിൽ ടച്ച് ചെയ്യുന്നു എന്നുള്ളതാണ്. ഓക്കെ, അതായത് നമ്മളൊരു വെരി ഷോർട്ട് ടൈമിൽ ആ ബോള് നമ്മൾ എന്താണ് അടിക്കുകയാണെങ്കിൽ അത് മോർ ടൈമിംഗ് ബോൾ ആയിരിക്കും. ഓക്കെ, ടൈമിംഗ് ആയിട്ടുള്ള ബാറ്റിംഗ് ആയിരിക്കും. അതായത് അതിന്റെ ഇമ്പൾസീവ് ഫോഴ്സ് ഹൈ ആയിരിക്കും. അതുകൊണ്ടാണ് അതിൽ തൊട്ട് കഴിഞ്ഞാൽ തന്നെ ഹയർ വെലോസിറ്റിയിൽ ആ സാധനം പോകുന്ന ബോള്, ടൈമിങ്ങിൽ അടിക്കുന്ന ബോള്. എന്നാൽ ചില ബാറ്റിങ്ങിൽ നമ്മൾ മോർ ടൈം ബോള് ബാറ്റുമായിട്ട് ടച്ച് ചെയ്യും. ഓക്കെ, അപ്പൊ അങ്ങനെ ആകുമ്പോൾ അതിലെ ഒരു ഇമ്പൾസീവ് ഫോഴ്സ് വരില്ല. അത് ഈസ് ലൈക്ക് എ സ്റ്റാറ്റിക് ഫോഴ്സ് പോലെ ആയിരിക്കും. അപ്പൊ അത് കൂടുതൽ ടൈം ബാറ്റിൽ ടച്ച് ചെയ്യുന്നതുകൊണ്ട് തന്നെ അതൊരു ഇമ്പൾസീവ് ഫോഴ്സ് ആയിരിക്കില്ല, അതിന്റെ വെലോസിറ്റി കുറവായിരിക്കും. ഓക്കെ, അപ്പൊ അത് അതിൽ കൂടുതൽ ഡിസ്റ്റൻസ് മൂവ് ചെയ്യില്ല ബോള്. Okay, similarly, ഇവിടെ നമ്മൾ ഈ ഹാമറിംഗ് ചെയ്യുമ്പോൾ മോർ ഇമ്പൾസീവ് ഫോഴ്സിലേക്ക് അപ്ലൈ ചെയ്യും. Okay, so that is impact load. We are applying impact load during the forging process. So this is the impact testing apparatus. So you are already familiar with this apparatus. This is in this apparatus we have a hammer. Okay, this hammer actually strike on this workpiece which is held here. Okay, or a swimming hammer ആയിരിക്കും. Okay, so two type of impact test ഉണ്ട്. Sharp impact test ഉണ്ട്, ISOT impact test ഉണ്ട്. What is the difference between these two tests? Sharp and ISOT. What is the difference? So in case of sharp impact test, see this figure. In this this is my workpiece. In this I provide a V notch here for stress concentration. Actually, we provide this V notch for stress concentration so that the fracture will always occur in this stress concentration region. Okay, and in this case of sharp impact test and ISOT impact test, the difference is only the support conditions of the sample. Okay, so here in this sharp impact test, we hold the workpiece like a simply supported beam. Okay, you can see this is the hammering direction, and here the workpiece is simply support is like a simply supported beam in case of sharp impact test. Okay, but in case of ISO test, we hold the workpiece like a cantilever beam. Okay, here this is the direction of the impact hammering, and we hold this workpiece like a cantilever. So that is the difference. That is only difference between these two type of tests, ISO and the sharp impact test. And this is our machine for this impact test, equipment for this impact test. And here, can you anyone can you explain this impact test, sharp impact test? നിങ്ങൾ ചെയ്തതല്ലേ? ഞാൻ തന്നെ പറയാം അല്ലെ ടൈം പോകും. So this is my hammer, and I position this hammer at a height of SI. Okay, SI height. And so during the time, what is the potential energy stored in that hammer? Potential energy, if the mass is M and the height is HI, then potential energy stored in this hammer will be equal to HGSI. MGHI. That is the potential energy stored in this hammer. And when I release the hammer, what happened? This hammer moves in this direction, in a circular direction, like a pendulum, and it strikes on this workpiece. Okay, it strikes on this sample piece. Okay, and because of the impact blow, what happened? This heavy mass fracture this sample, and then this hammer go back to this final position. It's like a pendulum movement. Okay, so some amount of energy which is stored in the potential energy which is stored in the hammer, that is equal to MGI, spent here to fracture this workpiece. Okay, the energy, potential energy, that is equal to MGHI. MGHI stored in this position is utilized to fracture this workpiece, and the remaining potential energy is actually used to move this hammer to this position. And in this position, what is the potential energy? The potential energy is equal to MGHF, because this is the height is HF from the datum. So MGHF is the amount of potential energy at this position. So the difference in potential energy from this position and the initial position and the final position will be the energy required to fracture this workpiece. Or we can say the energy absorbed by this workpiece for the fracture will be equal to MGHI minus MGHF. So Mg delta H is the amount of energy required to fracture the surface, or in other ways we can say energy absorbed by the material or workpiece to fracture under the impact load is equal to Mg delta H. Okay, so by this method we can calculate the amount of energy required to this fracture this workpiece, Mg delta H. So that is the sharp impact test or ISO impact test. Using this, we can measure the amount of energy required to fracture this material. Okay, any doubt? We use a V notch here. This is a V notch. That V notch is provided for stress concentration, so that we can fracture at this area, around this V notch area. So Mg delta H is by this test we can calculate Mg delta H. Mg delta H is the amount of energy absorbed by the material during the fracture. So here actually we are applying the impact load. Suddenly by this hammering, suddenly this heavy mass blow into this workpiece.
Sir, ഇത് അതിന്റെ thickness-നെയും എന്താ proportionate ചെയ്യാനായോ?
Yeah, here we use a standard specimen.
അല്ല, സ്പെസിമെന്റെ അല്ല, ഹെവി മാസ് ആയിട്ടുള്ള ഇതുണ്ടല്ലോ.
ആക്ച്വലി അതിന്റെ ഒരു പോയിന്റഡ് എഡ്ജ് ആയിരിക്കും. നിങ്ങൾ അതിന്റെ ഫീൽ കണ്ടിട്ടില്ല? ഇത് ഈ ഹെവി മാസ് എന്ന് പറഞ്ഞ ഒരു പോയിന്റഡ് എഡ്ജ് ആയിരിക്കും ആ വി നോച്ചിലുള്ള. ഓക്കെ, അതിലധികം തിക്നെസ് ഇൻഫ്ലുവൻസ് ചെയ്യില്ല. അതൊരു പോയിന്റഡ് എഡ്ജ് ആയിട്ടാണ് നമ്മൾ ഹാമർ ചെയ്യുന്നത്.
ഓക്കെ.
So this is called this is the Charpy impact test. Using that, we can find the toughness of the material. The energy absorbed, this mg delta H is the energy absorbed by the material, or we can say that is the toughness of the material. Okay. So by this test, we can measure or we can classify whether a material is tougher or not. Okay. If the material is tougher, then we can say that has enough strength and ductility. Okay. So next one is, so that is about the Charpy and ISO impact test. We can use this test to measure the impact load or fracture. So this impact test actually used in this area of ductile to brittle transition. This is a very important area in material science because I already in the introduction I have mentioned the failure of Titanic ship. Okay, and the main reason for this failure of the Titanic ship is because of the ductile to brittle transition. Ductile to brittle transition. So when we look on the history of the Titanic ship, that was a giant ship with a 46,000 tons of weight. Okay, and it has a 20 boilers for the propulsion, and it has a around 3K carrying capacity. Okay, so during the building time, unsinkable ship, unsinkable ship, a giant ship with the unsinkable ship. But of course, the design was perfect. Around 16 containers are used in that ship, like this. So this is a double hulled ship. Modern technology using the double hulled ship. Okay, so in the double hulled ship we have two protection plates. The hull ship in the hull 2 layers of sheets. Okay, in that there are 16 compartments. 16 compartments are there. So even 4 compartments are damaged. Remaining 12 compartments will be safe. Okay, so angane ship aanu. So design wise it was perfect, but there is one problem in that ship, that is the material used for making the rivets of the ship. That is the reason for the failure of the ship. So for the material which is used to make the rivet of the ship is wrought iron. Wrought iron. So already we discussed what is wrought iron. Okay, during the manufacturing of steel, the second stage was wrought iron making. Wrought iron. So this wrought iron is used to make the rivets of the Titanic ship. Okay, so what is the main problem for this wrought iron rivets? The main problem is this: in the room temperature or in the higher temperature, the wrought iron is behave like a brittle material, ductile material. It acts like a ductile material. So the fracture or failure will be a ductile fracture. That means after a severe or appreciable deformation, then only this ductile material fail. Okay, so in the room temperature or at a high temperature, the wrought iron behave like a ductile material. But under very low temperature, in the freezing temperature, this wrought iron behave like a brittle material. This behave like a brittle material, or the fracture will be like a brittle fracture. So what happened? So when we look on the journey of the Titanic ship, it started from England in April 10th, 1912, and the journey was from England to US. Okay, so during this journey, the ship has to cross Atlantic Ocean. Okay, so in this region, even in this region it was okay, but in this region, the temperature is in the freezing range. Okay, the temperature of the water is in the freezing range. We can see the icebergs. icebergs. Okay, so what happened in the freezing range? There is a transition of these wrought iron rivets from ductile to brittle. Okay, so what is the main reason for this transition? Temperature. Temperature. When the temperature is reduced, when the temperature is reduced to freezing temperature, what happened? The wrought iron changes from ductile nature to brittle nature. Okay, so in this area, so this is the area where ship collapsed or sinked. So in this area, the temperature was very low. Every wrought iron rivets converted to brittle material. Okay, so when the iceberg collide with this ship, what happened? You can see this figure. You can see this figure. When the iceberg, so this is the rivet. This is used to connect the two hull plates. Okay, so nowadays we are using welding for connecting this hull plate, but in the earlier days we are using riveted joints to connect these two hull plates. So what happened when the iceberg strike on this hull? What happened? See this, the hammering edge of this rivet failed because this one is a brittle material under low temperature. If it is a ductile material, okay, if it is a ductile material, such failure will not occur here. But because of very low temperature, these rivets, wrought iron rivets, converted to brittle material and it suddenly collapsed under the striking of these icebergs. And suddenly the water enter into the containment area of container area of the ship. Okay, that is the failure of the Titanic. So what I say is ductile to brittle transition. Ductile to brittle transition. So the material can transition from ductile material to brittle material based on the temperature, variation. And maybe there are other reasons also. The rate of strain increase. Okay, so the ductile to brittle fracture transition may occur with the temperature. So that is the reason for the failure of this Titanic ship. And other reasons are rate of straining increase. By increasing the strain rate also, the material may change from ductile nature to brittle nature. Or a notch or stress rises induced in the material also the reason for the ductile to brittle transition. So in this ISO test, we provide a notch. So that notch actually used to fracture in a brittle manner. Okay.
സാറേ സ്ട്രെയിൻ റേറ്റ് കൂട്ടി കഴിഞ്ഞാൽ സ്ട്രെങ്ത് കൂടുമെന്ന് നമ്മൾ നേരത്തെ പഠിച്ചായിരുന്നല്ലോ.
Yeah, strength increasing, but the toughness will decrease. Strength അല്ല toughness. Strength and ductility രണ്ടും കൂടിയാണ് toughness ആവുള്ളൂ. Okay. Strength increase ചെയ്യും. Especially അതിന്റെ എന്താ പറയുക അതിന്റെ വിയർ റെസിസ്റ്റൻസും അതല്ലെങ്കിൽ ഹാർഡ്നെസ് ഒക്കെ ഇമ്പ്രൂവ് ചെയ്യും. But the toughness affect ചെയ്യും. The rate of straining increase here, where the strain increase by severe hammering. By severe hammering, it may change into brittle nature. Okay, so these are the three reasons for the ductile to brittle transition. Okay, so this ductile to brittle transition is a very important factor while designing or while selecting a material for particular application. So in the case of Titanic, this very small rivets is the main reason for the sinking of the entire ship. The selection of the material was wrong. Okay, so this is the figure showing the variation of fracture energy. That means we already discussed for a brittle material, the fracture energy or the toughness is very low, but in ductile material it is very high. So when we decrease the temperature, we can see when we decrease the temperature, the fracture energy or the toughness is reduced. Toughness is reduced. That means in this region, at a higher temperature region, the material was ductile, but in the lower temperature region, it is changes to brittle. That is the ductile to brittle transition. So So here we can see the stress strain diagram. We already studied this stress strain diagram for brittle material and ductile material. This one for brittle material, there is no silent points here, proportionality, elastic, ultimate yield points here in the brittle material, only starting point and a fracture point here. And this is for a ductile material. Okay. So in this area under this graph is the low energy absorbed during fracture, or the toughness is very low. But here we have higher toughness for a ductile material. Significant plastic deformation before fracture. So what happened during the ductile to brittle transition temperature? There is a temperature, that is a transition region here. For some of the material, there is a specific temperature that changed from ductile to brittle. Okay, so under this transition temperature, what happened? The material changed from ductile to brittle. Okay, so that is very important. Already discussed the case of Titanic. So this is for a different plain carbon steel. What is the ductile to brittle transition temperature? Here we can see this is 0.01 weight percentage carbon. Okay, 0.01 weight percentage carbon steel. So in this case, this one around minus 10 or around this minus 10, higher than that of minus 10, it is ductile in nature. Okay, impact energy, it has a capacity to carry high amount of impact energy absorbing characteristics. That is ductile in nature. But when we reach this minus 10 value, what happened? It suddenly lost this impact energy carrying capacity, and it changes to brittle material. Okay, so in this 0.01 weight percentage carbon, it has a sharp or a constant temperature which changed from ductile to brittle material. Okay, but in case of 0.2 weight percentage of carbon, there is a transition region. It's a transition region for changing from ductile to brittle. So this is the transition region. Okay, we cannot say a specific temperature which changed from ductile to brittle. In this transition region, it's changing from ductile to brittle. Okay, but more specifically, based on the microstructure, we can say we can identify a constant temperature where it is changes from ductile to brittle. Okay, so that is the ductile to brittle. So this one is the average value, or based on the number of fibers according to the microstructure, we can say a constant temperature for the transition from the ductile to brittle. Okay, so this is another figure. This is another figure of different iron carbon materials. Actually, we plot this graph using Charping impact test, Charping or ISO impact test. We use different specimens under different temperature. Okay, and we conduct this Charping impact test. And based on that, we got this impact energy. We got this impact energy or energy absorbed during the mg delta H. That is this one, mg delta H. Okay, so we can do the experiment with the different samples and a different temperature. Based on that, we can draw this graph. Okay, so for this 0.01 percentage carbon, 0.11 percentage carbon, there is a sharp temperature for the transition from the ductile to brittle. But for this type of composition, there is no sharp region. Okay. This is another figure showing the transition from ductile to brittle. And here in this, for a material, a BCC material, this is for BCC material, this too. Okay, so for a BCC material, this graph showing the sigma y, that is the yield stress, and this graph showing the fracture stress. Okay, fracture stress. And here we can see at this point, the fracture stress and the yield stress is at a point. Okay, that means what it means, fracture stress and yield stress is common, means this one. For a brittle material only has same ultimate or fracture stress and yield stress. Both are same single point. But in case of this ductile material, this is the yield stress, this one is the fracture stress. Both are different. So here in this, by plotting this fracture stress and the yield stress, at this point, both are same. That means to the left of this point, it will be a brittle material. To the right, it will be a ductile material. Okay, and this type of ductile to brittle transition can only see in BCC material and HCP material. Okay, and this type of ductile to brittle transition is not visible in case of FCC material. Okay, so the FCC material does not show this type of transition from ductile to brittle with respect to the temperature change. Only BCC and HCP material showing this type of transition. Okay, so this is another curve showing the transition from ductile to brittle. So here we can see HCP and BCC only. FCC and HCP material has, we can see, with respect to temperature variation, there is no sharp decrease in impact energy. Okay, there is no sharp decrease. So low strength FCC and HCP metals does not showing any type of transition from brittle to ductile to brittle with respect to temperature change. Okay, but in case of BCC, we can see this blue line. BCC, we can see a sharp decrease in the impact energy or the toughness. Okay, so we have to select a HCP, HCC or HCP material when it is subjected to huge temperature variation. Okay, we should not select this type of BCC material because there will be a ductile to brittle transition. Maybe during the tensile test, it may show a ductile manner. The stress strain diagram will be like this, but during the impact test, it may show, it's depend upon the temperature, it show a brittle nature. Okay, and another type is high strength materials. This material has lower impact energy, but that is a brittle material even at any temperature. So ductile to brittle transition, FCC material do not show this type of transition. So this is good for cryogenic application. So for example, while developing a cryogenic engine or any cryogenic containers, refrigerator type containers, where we can use FCC material because under very low temperature, this FCC material can maintain ductile nature. The fracture will be ductile manner. Okay, and Osnate stainless steel is good for low temperature use because that is a FCC material, Osnate stainless steel. Even at a low temperature, it is a FCC material. But mild steel is not good for low temperature because mild steel from the iron carbon equilibrium diagram, we can say that is a ferrite, BCC structure. Okay, mild steel has a BCC structure, so mild steel is not good for a low temperature use because at a low temperature, mild steel changes from ductile to brittle manner or brittle failure. Okay, so mild steel is not good, but Osnate stainless steel is good at a low temperature. So we have to select a proper material based on this ductile to brittle transition. Another factor which is affecting this ductile to transmission and brittle transition temperature is grain size. If you use a finer grain size, lower the transition temperature. Okay, for example, in this material, if you use a grain size with a lower, if you make a material with a lower grain size, the graph may be like this. It may shift to even low temperature. Okay, so that we can use this material maintain the ductility in this range. So by decreasing the grain size, we can maintain this ductile behavior by finer grain size material. And high strain rate increase the transition temperature. So if you do more hammering on a material, that will increase the brittle nature or it shift the this line to the right. So even at a room temperature, it may behave like a brittle material. So this type of strain rate is a factor which affecting this transition temperature. Notches also increase the brittle behavior. Okay, these are the different factors which affecting this transition temperature. And structure change during ductile to brittle. What happened into the in the microstructure during this transition? So at a high temperature, the atoms in the material vibrate with a greater frequency and amplitude. Because the temperature is very, very high, the atoms are higher energy, so they will vibrate at a higher amplitude. And this increase allow the atoms to under stress to slip to new position within the material by breaking with the breaking a bond and rejoin or making a bond with another neighboring atom. Okay, so that breaking bond breaking and adjacent atom വീണ്ടും ബ്രേക്കിംഗ് ഫോം ചെയ്യും, ബോണ്ട് ഫോം ചെയ്യും. അങ്ങനെ അത് പ്ലാസ്റ്റിക് ഡിഫോർമേഷൻ ഉണ്ടാകും ഹയർ ടെമ്പറേച്ചറിൽ വിത്തൗട്ട് എനി ഫ്രാക്ചർ. So this slippage of atom is observed outside the material as a plastic deformation. That is a feature of a ductile fracture. But what happened when we reduce the temperature? How this change from ductile nature to brittle nature? So that is the answer is this. The atom may not be able to slip to new position in the material because the temperature is very small. Then the atoms has only less energy. So they need a higher energy to break the bond and reoccupy in another position. But the temperature is very small, so the atom will not break the bonds and occupy in the new position. Okay, it does not able to position in the new position. Okay, so the applied stress become higher enough. So what happened if we applying more stress? Then what happened? The atoms just break their bonds and do not form new ones. They completely break and finally a fracture is the fracture will occur. Okay, so that is the reason for the failure by brittle manner at a low temperature. So that is, this one is showing the microstructure for the material under different temperatures. And here we can see the appearance of the frailer surfaces indicate of the nature of fracture and can be used to transition temperature determination. By looking on this sample surface, we can say whether it is a ductile material or brittle material. Okay, so if it is a ductile fracture, what happened? The surface is like a fibrous and a dull shape. It's like this, fibrous and a dull shape. Okay, but if it is a brittle fracture, it will be like a shiny texture. A shiny texture is a brittle fracture angle, the material in the cross section. Okay, so by looking on these samples, fractured samples, we can say whether it is a ductile fracture or brittle fracture. ഇങ്ങനെ നമുക്ക് ചെയ്യാം, ഐസോ ടെസ്റ്റ് ചെയ്യാതെ. Any doubt about this ductile to brittle fracture? Ductile to brittle transition. So there are three factors. First one is temperature, second one is high strain rate, and third one is the stress risers, notches and other stress risers. Any doubt?